Okay, so let's say whatever it happens, stop me in half an hour. But maybe I lose the sense of the time, so at 12:30 we can stop. Okay, independently from where we are. So let's clean the board. So the next topic, okay, as we said, is super vector machines, SVM, which are still very, very not hot topic in chemometrics and machine learning. They have a lot of applications. Why? First, because they can be used both for classification and for regression. Okay, so we will have a look to super vector machine in a classification framework. Okay, but they can be adapted to working also for regression, and they can be used to separate classes in a linear way, as you see in this plot, but okay, by means of kernels, they can be used also to get not linear boundaries. Okay. Of course, when super vector machines are used in a not linear way, then things as usual get more complicated. But let's start from. We will start from the linear super vector machine, and then probably this afternoon we will see how to use it in a non-linear way also. Okay. It's always classification, so we have classes and we try to define a boundary between the classes to then classify a new sample. Okay? Another thing, super vector machine, okay, were proposed by Vapnik, I don't know how many years ago, maybe 20 years ago.
1991.
91, so 50 years
Okay.
ago. In the previous, let's say, version of super vector machine, they could model only two classes. Okay, so you can actually use super vector machine if you have two classes. Okay, but then of course you can somehow adapt. So we will see this super vector machine. Of course, then if you have more than two classes, okay, you can adapt super vector machine, okay, because you can do, but we will see at the end. You can do, you can model one class versus the others one at a time. And then you can like do, you can an ensemble of all these individual super vector machine models. But let's start from the very beginning. So we have two classes, okay, and we want to separate this class in a linear way, okay, with a linear boundary, okay? Okay, super vector machine defines this boundary, okay, trying to maximize the distance of the samples from the decision boundary, okay? So this is what they do, okay? And this is why they are called large margin classifier, okay? So they try to maximize, okay, the margin, so the distance of the samples from the boundary, okay, between the classes. So, for example, in this case, okay, this could be the boundary between the two classes, okay? And this boundary is found by super vector machine because this is the boundary which maximizes the distance of the red samples and the blue samples from this line, this tree. Okay? Then of course you use it as usual. So let's say you get a new sample. You don't know if this sample belongs to the class blue or the red class. let's say this sample is
You don't see the mouse.
I know. Let's say this sample is here. Okay, this is a new unknown sample. Okay, we will predict this sample as red. Okay. Now, how this separation and this margin is defined, okay, by super vector machines. So, which is the optimization function that super vector machine use, okay, to define this boundary, okay? And this here, things gets a little bit more fun, okay? So, let's try to simplify. We have two classes, okay? Red class and the blue class, okay? Is it okay for you if we code the red class as 1 and the blue class as 0? Okay? Red and blue can be anything, positive and negative, Italian and Spanish, good or bad. Okay? Bioaccumulable and not bioaccumulable. But we code the two classes as 1 and 0. Okay? So these are the class labels. Okay? For the samples. And, okay, these are the cost functions that are used by super vector machines. Okay? So, what does super vector machine do? It finds some coefficients. SPLSDA is very similar. I mean, it's different the way the coefficients are found. But then, at the end, you have a linear combination, can you see here, of your variables. Okay? And this linear combination is found by estimating some coefficients. So this is the coefficients for the first variable, this is the coefficient for the second variable, and so on. Okay? So we have this linear combination, okay? And we can write this linear combination in this way. This is a given sample of our data matrix, and this is the vector of our coefficients. Okay? We do this linear combination, okay? And we want, okay, this linear, we want to find some coefficients, okay, or better, super vector machine find some coefficients so that this linear combination must be, it's better if it's higher than 1 for the red class, okay, and lower than -1 for the blue class, okay, and this is exactly what you have here, okay, the cost function for the two classes, okay. Cost function means that we want to minimize, okay, these things. We want this to be as low as possible. What does it mean? That for the red class, class 1, okay, this linear combination must be higher than 1, because the cost is 0, right? If this linear combination is lower than 1 for this class, then you can see the cost is higher and higher. The opposite for the blue class. Okay? We want this linear combination to be lower than -1, otherwise the cost is higher and higher. Okay? This is the initial situation. So we want to find these coefficients, which then try to minimize these two cost functions. Okay? So, if we put these together, okay, we need an optimization function, Okay, so super vector machines try to find a set of coefficients, okay, that minimize, reduce all this stuff. Now, look at this first part, okay? This is what we have seen before, okay? This is the cost for the red class, class 1, okay? We want this to be as lower as possible, okay? This is 0 when this linear combination is higher than 1, you remember? Okay? This is the cost for the blue class, okay? Which was coded as 0, right? And even we want to be this cost as low as possible, okay? Let me see if you have understood. Imagine this situation, okay, where we have a very clear separation. So I expect all the red samples, okay, I expect to find some coefficients so that all the red samples have, okay, a linear combination higher than 1. And I expect that the same coefficients, okay, give me some linear combination for the blue class, which are always lower than -1, okay? Then, this part will be, this sum will be equal to 0, 1, 10, 100, 0, okay? Because this will be always equal to 0, and this will be always equal to 0, okay? This, of course, we will have overlaps in real data set, but we try to reduce this stuff, okay? Can you see this is a sum over all the, n is the number of training samples, okay? So we have to find, we don't find anything, but super vector machine find a set of coefficients that try to minimize this term, okay? But also try to minimize this stuff, okay? This is the sum, okay? This is called a regularization term, and we will see which is the effect of this stuff. But this is just the sum of the squares of the coefficients you have, okay? The lower the number, the lower the value of the coefficients, the better. Because the lower the coefficients, the lower this optimization function, okay? And we will see then in a graphical way what does it mean in the super vector machine framework to have low coefficients, okay? In a geometrical point of view. Okay? P is the number of variables you have. So you sum all the coefficients over all the variables you have. Okay? So far, easy. Okay? Now, can you see the two parts of this optimization function? Okay? But you also have this stuff, C. Okay? This is a positive number we have to define. It is called cost. Okay? So every time you do a super vector machine, you have to select a cost. Okay? It is this number. And it allows you to have a trade-off, okay, between this part of the optimization function and this one, okay, related to the length of the coefficients vector. Okay? So, if you use tuning this parameter, okay, changes the way, okay, we weight these two parts, and we will see again which is then the effect on a super vector of machine model. Okay? Of course, if this is very, very, very high, okay, if G is very high, 1000, we have to minimize this function. So we need this stuff to be very low. Okay? But we will see it later. Okay? This is the optimization function. So super vector machine looks for coefficients which minimize this stuff. Okay? Once a super vector machine has defined these coefficients, then what happens? You can classify a new sample, okay? Or a given sample, okay? You have your sample, you have the coefficients, okay? You do the linear combination, okay? If the linear combination is higher or equal to 0, then the sample is classified in the red class, okay, in the class labeled as 1. If the linear combination is lower than 0, then it's classified as blue. Okay, in the class we label it as 0. Again, this can be positive, negative, Italian, Spanish, good, bad, okay, male, female, whatever. Okay, these are the two classes we are modeling. Okay, so we use this, the 0, as the threshold of our classification. Okay, that's the threshold. But if you remember the cost function, we try to maximize this stuff. To not have, let's say, super vector machine tries to not have samples in this area, okay, in this margin. This is due to this optimization function. Can you see that? Okay, we say that when you predict a new sample, the sample is predicted as red 1 if the linear combination is higher than 0. Okay, but the cost function says that it is better if this linear combination is higher than 1. Okay, so we try to not have samples here, to maximize the distance between samples and the threshold between the two classes. Okay? And this is why they are called large margin classifiers. This is the reason why they are called in this way. Okay? Because they try to have a safety zone, okay, let's say, between the two classes. Okay? What time is it? Okay. This is what we said now, okay? This is what I already said now, but we can see it again. This is the optimization function. Okay? Here you have the regularization term based on the coefficients. Here you have the cost of the two classes. Okay? The sum of the cost over all the samples. The C. Okay? Cost parameter. Okay? These are the two cost functions we have seen before for the red class and for the blue class. Okay? And we said, okay, this is the cost function, so I try to have coefficients so that linear combination of red samples are give me values higher than 1, and for the blue class lower than -1, okay? And then I use the 0 as the threshold to predict, okay? This means having a margin, okay? A safety margin zone, okay? Between the threshold between the classes and my samples, okay? Is it clear enough? Okay. Let me know if something is not so much clear. Okay. Now, in order to understand, okay, which is the effect of C and the effect of this regularization term in a, let's say, geometrical point of view, let's do this assumption. Let's say that C, the cost value, okay, is very, very, very high. Okay? As I said you, this is a parameter we have to fix. Okay? Every time you do a super vector machine, you have to decide the value of C. Okay? So let's say we fix C to a very large value, 10,000. Okay? We have to minimize all these functions. So if this is very, very high, this must be very low. Let's say close to 0. Okay? And when this is close to 0, when all red samples, okay, have linear combination which is higher than 1, again, and all the blue sample have a linear combination which is lower than -1. When you have this case, right, you are here or here, all the cost functions are equal to 0, and this sum is equal to 0. 0 times 10,000 is 0. Okay? So let's say that we fix C to a very, very high value. Okay? The consequence is that super vector machine is supposed to find some coefficients, okay, which, okay, permit to have this situation. Okay? So this is the optimization function, but in this case, okay, all red samples with linear combination higher than 1, or blue samples with linear combination lower than -1, in this case, this term is equal to 0, so the optimization function is just that one, right? Only this part. Okay? You just have to look at this. And you have to minimize this stuff. Okay? So let's see, okay, what does it mean, this, in a geometrical point of view, okay, with super vector machines, okay? So let's say we have to find some coefficients, okay, which should be low, okay, because we have to minimize this stuff. Okay, if we have this situation, okay, there are a lot of possible boundaries, okay, between these two classes, of course, okay, and with all these boundaries, you can get a perfect classification, right? Because, I mean, you can perfectly separate the blue and the red samples, okay? But super vector machine will never choose one of these, okay? Because what we have to do, okay, at least what super vector machine do is to maximize, okay, the margin between the samples and the boundary between the two classes, okay? So this is, okay, the decision boundary between the two classes, which probably will be found by super vector machine, okay? Because this is the one which maximizes this margin. This is not, okay? Because here the margin is very low. And this is not, because here the margin is very low. And this is probably the one, okay? The optimal one for super vector machine, okay? And of course, if you use, I don't know, discriminant analysis or PLSDA on the same data set, maybe they would find something different, okay? Okay, so this is, look, the best option, okay? Because it has the highest margin. Okay? And this is the same situation we have seen at the beginning. Okay. I don't know what to do. What time is it? I think, yeah. Okay, let's do this last thing, and then we can stop before looking at geometrical consequences. Okay, in this case, okay, if you remember, we started saying, okay, we want to fix a very high cost value, okay, which implies that all the part in the optimization function related to the cost should tend to zero, okay? In this case, this would be the perfect, the threshold, it's not perfect, but the threshold found by the SOM, okay? What happens is that if you have an outlier sample, okay, in the training set, okay, like in this case, then super vector machine, okay, could, okay, if we use this very high chi value, okay, then super vector machine tries to reduce the cost for this sample also, okay, and thus it would find a threshold which is like this one, right? Because in this way the cost you have is minimum, okay? So if you have a situation like this, okay, super vector machine, maybe, okay, try to change a lot this discrimination threshold on the basis of this outlier, okay? So it can be sensible to the presence of a sample like this when we use a very high chi value, okay? If the cost value was lower, so we put less emphasis on that part, on the cost part in the optimization function, the threshold could change, okay? So this parameter can really leverage, okay, how super vector machine works, okay? And we will see later, but the higher C is, the higher the, let's say, possibility of overfitting is, okay, for this reason. Okay, while if we use a C, which is not too large, okay, we accept to have some cost. Let's say we accept to have some errors, and so The threshold we find with a C, which is lower than the previous one, could be this one, okay? Where we have some cost, of course, here, okay? With this threshold, the majority of the sample have a good margin, good distance between the threshold and then this one, but we accept it because, of course, there are errors, okay? Is it enough clear so far? How does it work? Okay. So, next we will see, but after the lunch break, in a geometrical point of view, how the optimization function works, okay? And how the threshold is defined and which is the dependence of the, in a geometrical point of view, of this optimization function on the basis of this step, okay? But I think we can do it in 1 hour after the lunch break, so you can a little bit think about this first part, okay? Yeah.